Hi guys, welcome to another one of RT Dowlett lectures, and today I will be discussing in a lot of detail the concept of electricity. Now, in one of my prior videos, I spoke about the introduction to what electricity is, and today I'll just be doing a brief revision of that, and I'll be going further into different concepts of voltage and resistance, and we'll be looking at Ohm's law. Okay, now when you talk about electricity, the last video spoke about static electricity, and in this video we're going to talk a little bit about current electricity. Now when we talk about a current, we talk about the rate of flow of charge. So charges originate within the atom itself, right? So when we talk about I, we could talk about either positive or negative charges flowing. And if you have a metallic conductor, right, a metal, they have negative or sea of negative charges already mobile. So what you will find is that when you have energy given to those charges, they will begin to flow. And that energy is deduced from a battery. So current is rate of flow of charge. So that charge is measured in the coulomb, C, and of course you're dividing it by seconds. The unit of current is called the ampere, and 1 ampere is 1 coulomb per second. So when we define rate of flow of charge, we can say it's either positive or negative charges depending on the medium. So if you have something like an electrolyte, for example, an electrolyte mobilizes both positive and negative charges, right, which move. So my current is measured in amps. So 1 amp is defined as the charge which flows for 1 second. And again, you can show your formula pyramid, Q over T, and you can solve for I from that, okay? So many times you might get a question, for example, determine the current when a charge of, let's say, 10 coulomb flows for, let's say, 2 microseconds. And sometimes they would like to do that. So when you talk about prefixes, you would see that this represents by 10 to the minus 6, right? So then you use your formula I is Q over T, which will be 10 over 2 by 10 to the minus 6. And you work that out, and your answer is in amps. Okay, so let's move on now to looking a little bit at voltage, because you would get more ideas on current from looking at my introduction video. So this is a follow-up video. So when we talk a little bit about voltage, we are talking about energy. And I want you to understand that a current will not flow if you do not have charges moving. So you firstly must have a substance, a medium, such as like a metal wire, where you do have charges being present. Or you can have an electrolyte where you have 2 kinds of charges. Now, for these charges to move, they must be given energy. So voltage is called or symbolized by V, and it is also called potential difference. That's another name for it, right? And voltage is defined as the energy or the work done to move a unit charge around a circuit. So what you will find is that V is equal to the work done to move a unit charge. So the work done is basically energy all the way over Q. So 1 volt, which is the unit, is 1 joule per coulomb. So that is your alternative unit. So it is the work done to move a unit charge around a circuit. So let's look at a typical circuit here. So let's say I have a bulb, I have a resistor. So this symbol here represents a battery. This represents a bulb. This represents a resistor. Now, your long stroke of your battery represents a positive terminal, and the short stroke represents your negative terminal. In a series arrangement, you will notice that at each point along your circuit, you would tend to have a potential difference. That is, the positive is connected to the positive here, and then all negative terminals or negative connections go to the negative terminal. Now, across these devices or components, you have a potential plus or minus arrangement. So it means that the potential difference across each component is what provides the energy. We conceptualize work done as force by distance, right? Now, the force that we are talking about are electrostatic forces. That is, if you have a negative charge, let's say this is a metal wire, so the flow of charge is due to the movement of electrons, you would typically expect that electrons will stem from the negative here and they become attracted to the positive terminal. Right? Movement of negative charges. So if you have electrons flowing here, then you can have electrons being repelled from this terminal and being attracted all the way to the positive terminal of the battery. So it means therefore that each device must have a potential difference across it in order to provide work done by providing a repulsive force against the negative terminal and an attractive force from the positive terminal to produce or allow your charges to flow all the way around the circuit. So what you will find here is that if you don't have a potential difference, then that attractive/repulsive force is not produced, and it does not provide work done or energy to sustain the charges being moved around the circuit. So it's like if I consider now positive charges, because in the previous video you saw conventional current being the movement of positive charges. So I can consider conventional current as well, where positive charges are repelled by the positive potential of the battery and now attracted to the negative terminal. So it is that difference that basically in essence produces a potential difference which kind of propels my charges around the circuit. Now, if you consider as well energy differences, you are seeing that from your battery you have chemical energy, and that is as your charges now flow in your circuit converted to electrical energy. When they go from your bulb, you have light and heat energy being produced, and then you have work done against your resistor in order to force your charges to go back to the negative terminal. So in addition to considering work being done, because that is what a voltage is, a potential difference, it uses attractive and repulsive forces in the circuit to propel charges to go all the way around. And there are different conversions of energy. So you have chemical to electrical, then electrical to light and heat, and then work being done across to get your charges across the resistor to now get back to the negative terminal. Now, when we consider voltage, I want to talk a little bit about cells as we're on the topic. Now, there are two kinds of cells. You can have a primary cell and you can have a secondary cell. Now, the battery that you use, like a AA and AAA battery, right, are examples of primary cells, and they are termed dry cells. And your car battery is an example of a secondary cell. Now, when you talk about your primary cells and your dry cells, these have a much smaller voltage, and a secondary cell will have a larger voltage. So the smaller voltage is around 1.5 volts, and for a secondary cell it's around 12 volts. So therefore you're going to have a larger current And then here you're having a a smaller current. I mixed it up here. You're going to have a smaller current, and then here you're going to have a larger current generated. You're going to have a smaller resistance, and obviously you're going to have a larger resistance. Next, these cannot be recharged. So when you use it and it's done, there's no more energy, you could throw it away. But these can be recharged. Like how you could jumpstart a car, that is what a secondary cell is used for. So you could talk about this cannot be recharged, but your secondary cell can't. And you have different components. So if you all have done electrolysis in the past, this is basically using the concept. So you would have your electrode, you would have your positive electrode being a carbon rod. You would have your negative electrode being a zinc casing. And you would have an electrolyte being ammonium 4 chloride. Here you would have your components. Your electrodes, your positive electrodes is just lead. Your negative electrodes is just lead. Oxide, and your electrolyte is sulfuric acid. So they basically consist of electrode in an electrolyte and electrolysis, which will be the process whereby your cells function. Now, one of the things you have to look at is a dry cell. Right? Now, your dry cell, and this is a popular diagram you need to learn. Has these components. It has a carbon rod, which is your anode, which is positively charged. You have a zinc casing, which will function as your cathode, negatively charged. Then here, just around the cathode, you have something called your depolarizer. Magnesium 4 oxide. And then between your depolarizer and your zinc casing, you have your electrolyte, ammonium 4 chloride. So many times you will be asked to draw this diagram, and you will be asked to talk about the cell, like the functionality of it. So here, remember how it works is that your zinc casing and you will be your cathode and your carbon rod is your anode. Now your electrolyte will have both positive and negative ions. Now if it is ammonium 4 chloride, then what happens is that all of the chlorine ions becomes attracted to the carbon rod. So the ions, the positive and negative ions in your electrolyte are now broken up. So the chlorine is attracted to the carbon rod and your ammonium is attracted to the zinc casing. Now, as a result of this reaction, when the ammonium breaks up, you have hydrogen ions being released. And you do not want a buildup of these hydrogen ions, which is why you have a depolarizer. So what a depolarizer does is that it's magnesium 4 oxide, and what it does is that the oxide reacts with the hydrogen to produce water. So it's not, a lot of students say, Miss, so is it that your cell leaks? I say no. They produce water in a form, not liquid state, but it's a kind of powder, dry powder. So what you will find is that when your battery is swollen, like if it's not used for a long time, right, what you will find is that that is as a result of the electrolytic reaction, and there's a kind of powder that is released from the electrodes, the edges of it. Now, the other option is your lead or your lead oxide cell, which is your secondary cell. And these consist of 6 2-volt batteries to give you 12 volts, right? And like your dry cell, it consists of, again, you have your electrodes being present here, right? So this would have been lead, and this would have been lead oxide, and your electrolyte would have been here, sulfuric acid. Now, the good thing about a secondary cell is that it can be reused because it can be recharged, and you are basically apply a current in the same direction as your electrodes, or how your current will flow in your circuit. So if you think about how you jumpstart a car, you connect the dead battery, quote unquote, to the one you want to, the functional battery. So you take positive to positive, and you could take the negative one and you ground it, right? So you basically ensure that the potential difference across the dead battery is the same as the functional battery, so that way you fool your car into thinking that it works. Now, the next thing I want to address is resistance, right? So when you talk a little bit about resistance, you are talking about a ratio of voltage to current. So R is equal to V over I. Now the unit of resistance is the ohm, the unit of voltage is V, and the unit of current is amperes, or E. So again, I like to show my pyramid where you have V over I is equal to R. And from this, you are able to say that V is equal to I, R. So if a conductor obeys Ohm's law in terms of it shows proportionality. If voltage increases, current increases, and R is constant. Let's talk a little bit about that. So if it is that my voltage increases, my current increases, and that makes total logical sense because we conceptualize voltage as energy, right? So if it is that you have a lot of energy being given to the charges, then what will happen to the charges? They will begin to move. So the greater the potential difference is, the greater the rate of flow of charge, right? So what you will find now is that if you have a greater rate of flow of charge, then you will have a larger current being produced. Okay? So R will work out to be constant. So V is proportional to I. Now normally we could show an IV graph, right? And it will be a straight line. Or I could show a VI graph, and that is also a straight line from the origin. Now if I represent I as the subject of the formula, it's 1 over R multiplied by V. So this could be in the form Y is mx plus C. So here, if I plot a graph of I versus V, the slope of my graph becomes 1 over R. If I plot a graph of V versus I, the slope of my graph is represented as R. Okay? Now, If we talk about a filament lamp, then we are talking about an IV graph that represents a relationship like this. So eventually you can get the tangent to different points along the graph here. So you're looking at point A and you're looking at point B. So this represents 1 on R. So 1 over R at A is greater than 1 over R at B. So it means that your resistance, well, your gradient, I should say, decreases. So 1 over R decreases, so R increases, right? Now what you find here is that in a filament lamp, you have a material called tungsten being used in the filament. And what happens is that as your current flows through this tungsten wire, it causes it to get hot. And when tungsten becomes hot, it begins to glow. So you will find basically that when the tungsten wire begins to, like the current flows through it and it starts to get really hot, then it begins to glow and emit a lot of light energy, right? And you will find that eventually the resistance will increase, so it will glow up to a certain value. Okay, so this brings us to the end of this video, and my next video I'll be looking at series and parallel circuits.